Yes, my screen is visible.
Yes, sir.
Okay. Yeah. So now, so we will discuss about the PN junction. Yeah, it's Zener diode today. Okay. So before going to that, so just we'll refer yesterday class once again. Okay. So we are discussing about the forward bias and reverse bias and IV characteristics of the PN junction. We are discussed as well as, so this is the equation. This is the equation of PN junction diode. Equation of PN junction diode. This equation is applicable for both forward bias and reverse bias. Okay. So depends on the voltage. V is the voltage drop. That means voltage across the diode or applied voltage. Simply whatever the through battery we are applying now, that is the applied voltage Vd here. So neta by Vt. Okay. So by using this formula is applicable for both forward bias and reverse bias. So how much current is passing if you that means if PN junction diode is connected in forward bias, how much current is passing if PN junction is connected in reverse bias. By using this formula we can calculate it. So that this equation we will call it as Shockley equation. Okay. So how to convert this equation into forward for reverse bias and for reverse bias and forward bias we will discuss just now. So for that I am showing here. Okay, 1 minute. So this is the equation here. So previous equation is here we are showing. So this is the id is equal to is into so e power vd by neta into vt. So already I said that vt means kt by q. Here q is the charge of the electron. So instead of q we can write e also. So substitute this et value above equation. So we will get the so this equation only. Okay. So I is equal to instead of so here I naught we are taken I naught into e power so EV by neta kt minus 1. This is the equation. Okay, this is the equation in case of diode. So how much current is passing through the diode. Okay, so here I naught is we know that that is the reverse saturation current. Okay, V is the applied voltage or voltage potential difference. Okay, so potential difference of the diode or potential drop across the diode. So simply so whatever the we applied the voltage, so that also so V. Okay, and neta kt, k is the Boltzmann constant, t is the temperature. Okay, now see here. So neta is the, what is the neta? Already emission coefficient I told that emission coefficient neta is equal to 1 for germanium and 2 for silicon. Okay, so neta is the emission coefficient. So that emission coefficient value n equal to 1 for germanium and n equal to 2 for silicon. Okay, now so we will discuss how for it will be reverse bias and forward bias. Okay, so first of all we are taking the forward bias. So what is the current passing through the forward bias? We will calculate now. So according to this, so here in case of forward bias, so this V means applied potential. So V value will be greater than 1. V value will be so greater than 1 in case of forward bias. So that voltage is applied voltage is so positive. Applied voltage is positive. That's why EV by neta kt. EV by neta kt is greater than 1. Greater than 1. Okay. So EV by neta kt is greater than 1. So that means EV by neta kt is greater than 1 means E power EV by neta kt is very greater than 1. EV by neta kt is greater than 1. So E power EV by neta kt is very greater than 1. So that's why, so compared to this value, so this 1 will be very small. 1 will be very small. That's why we can neglect this one. Okay. So that's why, so in case of forward bias, simply, so for in case of forward bias, current passing through the circuit IF is equal to, so I naught into EV by neta kt. Okay, so what we are doing means just we are neglecting the 1. So what is the reason means, so here V value is greater than, so V value is positive. So that's why EV by neta kt is so greater than 1. EV by neta kt is greater than 1. Okay, so that's why if you will take so forward current equal to IF is equal to I naught into EV by neta KT. So this is in case of forward bias, how much current passing through the diode. Okay, this is the equation for forward bias current. Okay, now coming to the reverse bias. So reverse bias here. So in case of reverse bias, so in this equation, voltage value will become so negative. So we are applying opposite direction. Voltage will we are applying opposite direction. So that's why EV by neta KT is small. EV by neta KT. So this is so minus EV by neta KT is small. Okay. So that's why this total value we can neglect. So this is e power some small value means so we can neglect that total e power. So this what is that exponential? This exponential value we can neglect. So that's why so this total value will we are neglecting. So final equation will become IR is equal to minus I naught. IR equal to minus I naught. So what is the current passing through the reverse bias? So that is the reverse bias. What is the current passing? So that is I naught. That means in reverse bias up to breakdown voltage. So the current passing through the diode is constant. Current passing through the diode is constant. That current we will call it as reverse saturation current. Reverse saturation current. So in case of diode, so if you observe the reverse bias, so that current is constant up to breakdown voltage. So what is that constant current means? So that is I naught. That I naught we will call it as reverse saturation current. Okay. Now after breakdown, what happened? That current will increases drastically. After breakdown voltage, that current will increase drastically. Okay. So this is the what is that Shockley equation for so forward bias and reverse bias. Shockley equation for forward bias and reverse bias. Okay. Now coming to the effect of temperature we discussed yesterday. So how it will be affect with increasing the temperature and in forward bias. Okay. So what happened here with increasing the temperature? So in this direction. Okay. So the threshold value. So threshold voltage. Who is that? Who is that? 5E3. What are you doing? E3. Yes. Mute yourself. E3. So what you are doing? Nonsense things. Okay. Now coming to the here. Okay, so with increasing the temperature, in case of forward bias, in case of the PN junction diode, forward bias. So if you increase the temperature, what happen? We are discussed already. So once again, I will explain you. So if you observe the lower temperatures, very lower temperature, that means less than room temperature. So it will be like this. So here, what is that? So threshold voltage or knee voltage will be very high. Threshold voltage and knee voltage will be very high. If you increase the temperature, what happens? That threshold voltage is decreases. What is the rate of decreasing? So minus 2.5 millivolts per degree centigrade. Okay. If you increase the each 1 degree, if you increase the each 1 degree temperature, what happen? So that voltage, what is threshold voltage will decreases minus 2.5 millivolts. Okay. So if you observe at room temperature, yes.
Sir, is the temperature is inversely proportional to the applied degree, sir?
Inversely proportional to the here. What is that threshold voltage? Temperature is inversely proportional to the threshold voltage. Okay. So with increasing the temperature, threshold voltage is decreases. Threshold voltage or knee voltage is decreases. Okay. So what is the rate means? So it will be minus 2.5 millivolts per each degree of temperature, each degree centigrade of temperature. Okay, here I will explain you how it will be. Okay, so with increasing the temperature, it is decreases. Okay, see here. Here, so initially we are taking at 25 degrees centigrade. Initially we are taking at 25 degrees centigrade. So and we are increasing the temperature 80 degrees. 80 degrees centigrade. So how much threshold voltage will be decreases? How much threshold voltage will be decreases? Okay. So what is the changing here? So 80 minus 25. 80 minus 25. So that means total how much here? So 80 minus 25 means total 55 into 2.5 into 2.5. So that means per each degree 2.5 millivolts. So that's why. So how much total? So 137.5 millivolts. Okay. So here let us take. So let us take here threshold voltage will be X. Threshold voltage will be X. So suppose we are taking at 25 degrees now. So at 25 degrees, so threshold voltage will be X. Okay, we are increasing the temperature to 85 degrees centigrade. 85 degrees centigrade. So what is the threshold voltage means? X minus, so 135. Okay, whatever we got here, so 137.5. X minus 137.5. Okay, so that much of voltage is decreased. That much of voltage is decreased. Okay, now this is about in case of forward bias. Okay, now coming to the reverse bias. So silicon or germanium. So for every 10 degrees centigrade increasing of temperature, what happened? So here reverse saturation current. First of all, we will discuss about the reverse saturation current. That reverse saturation current will become double. Okay, so reverse saturation current will become double. Okay, so now let us take here. So let us take, we are taking it 25 degrees centigrade, same. So it will be 100 nano amperes. So reverse saturation current is 100 nano amperes. Okay, and similarly, so we are increasing up to 85 degrees centigrade. We are increasing up to 85 degrees centigrade. That means the difference between these two is 60 degrees. Okay, that means we are increasing here, temperature is 60 degrees. So according to our statement, each 10 degrees, what happened? Reverse saturation current will become double. Okay, each 10 degrees centigrade, that reverse saturation current will become double. So that's why this 60 we can divide it into 6 grades. Okay, 6 parts. Okay, so that means 6 parts means, so here n is 6. N is 6. So according to the formula, so it will be how much time that the reverse saturation current will be increases means 2 yeah, so 2n power 2, 2n power 2. Okay, 2n square. According to the formula, so how much? So this reverse saturation current will be increases means 2 into n square. 2 into n square. Here n is the 6 gradients. We are dividing that 60 degrees into 6 gradients. Okay, so that's why. So here n equals 6. So if you apply the formula, so 2 into 6 square means 36. That means how much it will be increases means 64 times. So initial current is 100 nano amperes. If you increase the 60 degrees, so how much time increases means 64 times it is increases. Okay, so 100 into 64 means 6400 nano amperes. So that reverse saturation current will become 6400 nano amperes. Okay, so this is about the reverse saturation current in case of reverse bias. In case of reverse bias, so simply so not using this formula, how you can divide means, suppose here increasing 25 to 35 means it will be double means 100 will become 200. So 35 to 45, so it will become 400. So 45 to 55, it will become 800. So 55 to 65, it will become 1600. So next 65 to 75, it will become so 32, 3200. So similarly, what is 75 to 85? It will become 6400. Okay, so that formula is correct now. So 2 into n square, it will become 2n square times. Okay, so that's reverse saturation will current will become so 2n square times. Okay, now coming to the, so in the graph, so if you observe the graph, so if you observe at room temperature at 25 degrees centigrade, this will be like this. So at a higher temperature, it will become like this. So that reverse saturation current will become, so increases with increasing the temperature. Okay, so now coming to the yeah. So here one more thing we have to discuss here, threshold, sorry, breakdown voltage. So in case of reverse bias, so what we will call at a particular temperature, the current will be increases suddenly. At a particular voltage, the current will increases suddenly. That voltage we will call it as threshold voltage. Okay, the threshold voltage also increases with increasing the temperature. Increases with increasing the temperature. Okay, so this is about the in case of reverse bias. Okay, reverse bias, forward bias characteristics of the so diode. Okay, so these are the some applications here. So first application is used as a uh, what is that, rectifier to convert AC into DC. Okay, so because so this diode act as so forward bias in case of positive terminal. So if you apply the positive voltage, and reverse bias in case of if you apply the negative voltage. That's why, so that means if you will take AC current, there is a positive half cycle will be there, negative half cycle will be there. For positive half cycle, it will become forward bias. Okay, for negative half cycle, it will become reverse bias. So that's why it allows only positive half cycle. So that's why, so DC is nothing but, so there is no fluctuations in current. So that's why, so only one direction current will be passing. Okay, AC means alternating current here. So that's why this, what is that, diode rectifies. So one half cycle, rectifies one half cycle. That's why we'll use it. So in rectifiers to convert the AC current into DC current. Okay, and it will be used as a switch in computer circuits. Okay, so switch means for forward bias it will be act as a conductor. It will, for reverse bias it will act as a insulator. So that's why, so we can use it as a switch in computer circuits. Okay, next, so detector in radios detect the audio signals. So by using detector we can tune the particular signals, we can tune the so particular signals. So that's why, so we can use the this diode in to detect the audio signals. Okay, and used as a LED, used as a LED in, for emitting the different colors, for emitting the different colors. Already we discussed in what is that, recombination and emission process. So on that emission process, what happened? So that electrons jump from conduction band to valency band, conduction band to valency band. So while jumping the electrons, what happened? So it loses some energy. It loses some energy. That lost energy is converted into a light based on that phenomena. So based on that phenomena, here LED will works. LED will works. So this is the application of the diode. Okay. Now coming to the, we will discuss about the Zener diode. Okay, Zener diode and its IV characteristics of the Zener diode we will discuss. Okay, so first of all, what is the Zener diode? Okay, a Zener diode is a specially designed, highly doped PN junction diode. Okay, it is similarly, so nothing but PN junction diode only, but it is highly doped PN junction diode. So in N region as well as P region, it will be doped very highly. N region as well as P region, so it is doping with the highly. That means, so doping is nothing but we are, for N region we are adding pentavalent doping element. Similarly for N region, so for N region pentavalent, for P region so trivalent element we will dope. Okay, so like that, so heavily we have to dope here. Okay, so that is the difference between the normal diode and so PN junction diode, and normal diode and Zener diode. Normal PN junction diode and Zener diode is, in case of normal diode, so doping is normally it will be doped. So but in case of Zener diode, it will be doped very heavily. Okay. Next point, Zener diode is a semiconductor diode specially designed to operate in the breakdown region of the reverse bias. Already we discussed about the breakdown region. So for operating, so if you observe the normal diode, so if you operate normal diode at breakdown region means it will be damaged. It will be damaged. So but Zener diode does not damage. Okay. So we'll discuss why it will not damage. So at if you operate at breakdown voltage. Okay. Now in Zener diode, the breakdown phenomena is reversible and harmless. Okay, now only just we discussed. So in Zener diode, that breakdown phenomena. So in normal diodes, so if breakdown point will occurs, if breakdown voltage, so if applied voltage is greater than the breakdown voltage, what happen? Normal diode will collapse. But so Zener diode so works at breakdown voltage, works at breakdown voltage. Okay. Uh, okay, and so in case of normal diode, if once covalent bond will breaks means so that diode will collapse. But here, so breaking of the covalent bonding is so there is a what is that reversible phenomena. So after breaking the covalent bond, again it will form the so bonding. Okay, so there is no damage of material in case of Zener diodes. Okay, we will discuss why it will not. So it will not why what is the reason also we will discuss. So why it will be reversible process also we will discuss, why it will be harmless also we will discuss. Okay, and a Zener diode is a type of diode that permits current not only in forward direction like normal diode but also in the reverse direction if the voltage is larger than the breakdown voltage is called as Zener diode. Okay, so in case of if you observe the so Zener diode, so this forward bias of Zener diode is similar to the PN junction diode. PN junction diode. But now coming to the reverse bias. Now coming to the reverse bias. In case of reverse bias, if you will take the normal diode, what happen? So after breakdown voltage, so that PN junction diode, normal PN junction diode does not work. But so in case of Zener diode, so at reverse breakdown voltage, so it works on breakdown voltage. It works on breakdown voltage. Okay. So when the reverse voltage above the Zener voltage is applied to a Zener diode, there is a control breakdown which does not damage the diode. In the Zener region, the voltage across the Zener diode remains constant, but the current changes depending on the supply voltage. Okay, so now here we are observing here. So that means if you will take the Zener diode, yeah. So I will take the diagram here, circuit diagram. Suppose here we are applying some external voltage. So this is the reverse bias. So here we are applying some external voltage. Okay, if you apply the so what happen if you increase the voltage, what happen here? So up to particular voltage, this reverse saturation reverse current will become so constant. Okay, that current we will call it as reverse saturation current. Okay, after that what happen? That current will increases drastically. Current will increases drastically. So this is the applied voltage. So what happened? So whatever the applied voltage is there here, so that will become as a diode voltage. So in case of normal junction, normal diodes, suppose here, so if you are applying 10 volts, so what is the voltage across the diode? Similarly 10 volts only. If you are, so that means at 10 volts, what happened? Breakdown will occur. Breakdown will occur in case of normal voltage. So what happened if you apply the 15 volts means, so this will damage. This will damage. Okay, now coming to the in case of PN junction diode. In case of PN junction diode, what happened? Suppose so in case of suppose if you apply the so 15 volts. So here threshold voltage is what is that? Breakdown voltage of the Zener voltage or breakdown voltage of the Zener diode is 15 volts. Let us take. Now we are applying the 15 volts. Okay. So here if you observe this means voltage drop across the diode is same 15 volts only. But if you increase the voltage here, if you increase the voltage 20 volts, applied voltage is now what we are doing, so 20 volts. So if you observe the Zener diode, so voltage drop across the Zener diode is so now 15 only. 15 only. It will not increases. It will not increases. Okay. So what is the reason? We will discuss. Okay. See here. So in case of normal diode, what happened with increasing the voltage? So voltage drop across the diode also increases. But in case of Zener diode, if you increase the external voltage also, voltage drop across the Zener diode does not increases. Does not increases. It will be constant at the breakdown voltage. It will be constant at breakdown voltage. So based on this phenomena, based on this technique, so our suppose so our refrigerator works at a particularly 220 degrees centigrade. Suppose if voltage is coming at 240, what happens? Refrigerator will damage. If you use the PN junction diode, what happens? So it allows only 220 volts, 220 volts. Okay, so like that. Suppose washing machine, everything, TV, so everything it will be operated at a particular temperature. If you increase the more than the temperature means what happens? They can damage. Okay, sometimes in our houses current fluctuations will be coming. So for controlling that current fluctuations, so what we will use means, so we'll use the Zener diode. That means Zener diode used as a voltage regulator. Zener diode will be used as a voltage. Okay, so what we are discussing here, this only. So control breakdown. Okay, in the Zener region, the voltage across the Zener diode remains constant, but the current changes depending on the supply voltage. So current may increase. Okay, but so voltage will constant. Voltage remain constant. Okay, so in case of Zener diode, voltage drop across the Zener diode. Remains constant. This is the important one. Okay, so so we are supplied voltage, so voltage drop across the Zener diode remains constant. Okay, so but current may increases. Now, so what is the symbol of Zener diode? So this symbol will be same as a normal diode only, but in cathode region. There is a one line will be there. That line will be bended on both sides like Z, Okay, that symbol will be so like this. See here. Okay, so this is the anode and this is the cathode. So that here cathode is represented as a line, anode will be represented as a like this triangle. Okay, so now what is the difference between symbol for normal diode and Zener diode means at cathode region that line will be bended. Like a shape of Z. Okay, Z. Okay, so that's why. So this is the representation of Zener diode. Okay, so here so many Zener diodes, so many range of Zener diodes will be available. So many ranges of Zener diodes will be available. Okay, so if you want to increase the particular voltage means they will connect in a series or parallel. So depending on the connection, so we can increase also. Okay, so we can make particular voltage will be constant. Okay, for that depends on the so voltage what we need. So for that they will be so several one or two or three several these Zener diodes will be either connected and series or parallel, and they will make a particular whatever the voltage we need. They will make the particular voltage constant by using this Zener diode. Okay, next IV characteristics of the Zener diode. So I will explain you that is what is the Zener breakdown. Okay, what is the Zener breakdown? So after this forward and reverse bias. Okay, first we will discuss about the so forward bias characteristics. Okay, so Zener diode acts very much similar to ordinary diode under forward bias condition. Okay, so what are the characteristics means similarly whatever it will be there in forward bias PN junction forward bias characteristics, so whatever it will be there, so that for the so Zener diode also same. Okay, so now reverse characteristics. So in case of reverse characteristics, as we increase the reverse voltage, initially very small reverse saturation current flows due to the minority charge carriers. So whatever we discussed previously, that only. So initially, what happened? Very small amount of current is passing. That current also constant current. So passing through the diode. So what is the reason for that current means due to minority charge carriers. Okay, at a certain value of reverse voltage, the reverse current will increase suddenly and sharply. So this is an indication that breakdown has occurred. Okay, at a certain value of voltage, the current the reverse current will be increases suddenly and sharply. This is indication that breakdown has occurred. So this breakdown voltage is called Zener breakdown voltage or Zener voltage. It is denoted by Vz. Okay, see here. So this is the diagram here. So up to particular value, what happened? Current will become constant. So the current will become constant. That current we will call it as reverse saturation current. Okay, if you increase the voltage up to particular voltage, that current is constant. Okay, so and after that voltage, what happened? That current will increases very drastically. Current will increases very drastically. See here. So if you observe that, so up to particular voltage here 0 to Vz, so current is constant. So after that, so current is increases very drastically. So if you observe the normal diode, okay, that observe the normal diode. So here also, so current is increases drastically, but so after Vz, what happened? So this will damages. Zener diode normal PN junction will be damages. Okay, but in case of Zener diode, it will not damage. It will not damage. Why it will not damage? Also, I will explain you. Okay, so this is if you increase the current up to 0 to Vz, so current is constant. After Vz, that is the Zener voltage. What happened? Current will increases drastically. If you increase the so further, if you increase the further voltage also, so here voltage increasing voltage is nothing but applied voltage. Okay, if you apply the further voltage also, what happened? So diode voltage will become constant. Diode voltage will become constant. Zener diode voltage will become constant. That means so whatever the we are after Zener breakdown voltage, after breakdown voltage, so whatever the we are supplying the external voltage, whatever the we are supplying the external voltage, so but that Zener voltage does not changes. Zener voltage does not changes. Okay, so but current is increases. But current is increases. Okay, so this is about the so what is that characteristics, reverse characteristics of the Zener diode. So forward bias characteristics is similar to the same. So whatever the PN junction diode will be there, so that only. Okay, but reverse. So this is the breakdown region. Whatever it will be there. So this is the breakdown region, Zener breakdown region. Now applications of Zener diode. Some applications of Zener diode we will discuss here. So Zener diode have a large number of applications. Few of them are we will discuss here. Okay. So Zener diode is used as a voltage regulator. Just now only we discussed how it will be worked as a regulator. How it will be means if you increase the external voltage also, Zener voltage does not increases. Does not increases. So that's why it will be used as a voltage regulator. Okay, and second one, Zener diode is used as a peak clipper in a wave shaping circuit. Okay, so peak clipper means suppose we want a particular suppose if you will take sine wave, if you will take sine wave means what happen, it will be so that amplitude will be certain value will be there and below also certain amplitude will be there. Okay, we want only particular amplitude, we want only particular amplitude. Suppose initially that voltage, suppose if you will take voltage also, it will behave like a sine wave only. If you will take AC voltage, it will behave like a sine wave only. So but we don't want higher voltages, so that amplitude we don't want higher amplitudes, higher amplitudes, we want only particular amplitudes. Suppose that amplitude is approximately 55 volts will be there, so but we want only 50 volts. 50 volts means what will do means if you will take the Zener diode, if you will apply the Zener diode means so it will allows only up to 50 volt. So if you adjust the Zener voltage to 50 volts, so what it will do means it will be allows only up to 50 volts. So whatever the peak value will be there, so 55, 50 to 55, it will be clamped. It will be the clamp. Okay, that's why what happened here. So by using Zener diode, so that allows only particular voltages, particular voltages. That means it will be used as a clipper, clipper in a wave shaping circuits, wave shaping circuits. Okay. Now next one is Zener diode is used as a fixed reference voltage in transistor biasing circuits. Okay, so while using the transistor, so whatever the we want the voltage, so we can supply the fixed voltage by using Zener diodes. Next one is Zener diode is used for meter protection against damage from accidental application of excessive voltages. Okay, so like voltage regulator, suppose so that means if excess voltage will come means may damage circuits, our systems are may damage. Okay, so by using Zener diodes we can protect from the excessive voltages. So that's why we can use as a damage protector, accidental damage protector. So these are the some applications of Zener diode. Tomorrow we'll discuss about the what is the Zener breakdown and avalanche breakdown also there. So what is the avalanche breakdown? So we will discuss regarding about these two. Okay, so this is Zener diode also very important one. Okay, of the class, just read once. Okay, so any doubt on this? First of all, I will take the attendance. Okay, now you can leave. If you have any doubt means you can ask, otherwise you can leave from the session.